Do you ever go fossil collecting? Even if you aren't an expert, fossil collecting can be a lot of fun, and you never know what you might find. You might find something amazing. But what if you wanted to go looking for something in particular? Let's say trilobites. Where would you go to find trilobite fossils? How would you know where to search? Trilobites were arthropods, meaning they were relatives of crustaceans and insects. They lived in the ocean, and although they are all extinct now, they were particularly common during the Cambrian period. Indeed, some trilobites are considered index fossils for the Cambrian. So it stands to reason that you could find trilobites in rocks of Cambrian age. Now what? Where can you find Cambrian rocks? Where do you begin? In fact, there are many ways you could proceed, but the best way might be to look at a geologic map. Geologic maps illustrate where rocks occur on the surface of the planet. William Smith, a pioneering English geologist, created the first large-scale geologic map in 1777, as well as the first nationwide geologic map of any country in 1815. In this case, it was a map of Great Britain. Since then, geologic maps have come a long way. They have evolved into some of the most important, fundamental, and sophisticated tools available to geologists and amateurs alike. All maps contain certain basic elements which can help you make sense of them. The body of the map illustrates where rocks occur on the surface, and in cases like this, in the subsurface as well. The bodies indicate the lithologies and facies of the rocks, as well as the names of the stratigraphic units, like the members, formations, and groups. Maps also have titles and legends. The title is short and informative. It tells you what you are looking at. And the legend provides the key to understanding it. What do the colors mean? What are the lines? What other structures are apparent? You can determine the answers to these questions by looking at the legend. There is also usually a scale bar, which tells you how real distances are represented on the map. And of course, you can find information on the source or origin of the map, who produced it, and how. And most maps, like this one, also have a grid, which can be used to determine the geographic coordinates of locations. Most maps use the standard geographic coordinate system, where coordinates are latitude and longitude. Latitude is measured along horizontal lines called parallels, and longitude along vertical lines called meridians. Both are reported in degrees, measured from datums, latitude from the equator, and longitude with respect to the prime meridian, which passes through Greenwich in the United Kingdom. Latitude varies from -90 to +90 degrees, and longitude from -180 to +180 degrees. Geologists often want to know about the physical features and variability of terrain. The surface of the Earth, after all, is not smooth. One of the most important features of terrain is elevation. Elevation is the height of terrain measured from a specific datum, like sea level. The elevation of terrain at sea level is 0 feet. The elevation of the peak of Mount Everest, the highest point on Earth, is 29,029 feet. The depth of the Mariana Trench, the deepest point in the ocean, is 36,070 feet. So, all elevation values on Earth fall in the range of negative 3670 and 2929 feet. Elevation values are used to define the relief or topography of the planet's surface. Textbook examples of topography are canyons, valleys, and mountain ranges, all of which add to the variation of the planet's surface. On a geologic map, topography is illustrated as contour lines. Contour lines are a series of smooth, non-intersecting lines on a map that represent changes in elevation in regular intervals. A contour line connects points of equal elevation. If you were to walk along a contour line, you would not go up or down in elevation. Contour lines are provided according to a contour interval, defined for a map as the distance in elevation between lines. In this case, the contour interval is 100. Tilted strata can add to the complexity of the terrain in the body of a map. To visualize the orientations of strata, maps include measurements called strike and dip. Strike and dip measurements are commonly illustrated with this symbol. The symbol consists of the strike, which is the line with 2 free ends, and the dip, which is attached to the strike at a perpendicular angle and has 1 free end. The strike of a formation represents where that formation intersects with the horizon. It is also considered to represent the trend of the formation. The accompanying dip represents the direction in which the formation dips downward. There is often a number associated with the strike and dip symbol, as shown here. This number is the number of degrees down from the horizon that the formation is dipping. Strike and dip measurements are very useful for identifying the presence and locations of angular unconformities in a map. Angular unconformities are obvious when rocks have different strike and dip measurements, even though they occur near each other. Not surprisingly, geologic maps also visualize faults. Recall that faults are fractures where rocks are able to slide past each other. This sliding creates mismatched sequences on opposite sides of the fault. The rocks, the strata, appear offset. Faults are depicted in maps as thick lines separating different sides of the fault zone. Strata on opposite sides of a fault may have similar sequences, but appear offset from each other. They may also differ in strike and dip measurement. Finally, geologic maps visualize folds. Folds are places where tectonic activity has caused rock layers to compress, bend, and contort. Such folds can be viewed in both maps and in cross-section. There are 4 important types of folds. Domes are rounded summits, like hills and mountains. They rise upward from the surface. The rocks dip away from the summit and the oldest rocks are located in the center. Basins are the opposite. They are rounded, natural depressions sunken into the planet, where strata typically dip toward the center and the youngest rocks occur in the center. An anticline is a type of arch-like fold where the oldest rocks occur in the core. In a map, an anticline looks like pairs of repeating stripes nested around a single strip in the middle. Synclines are the opposite. The youngest layers occur in the core. Armed with a high-quality geologic map, everything becomes clear. Where are the rocks, and why are they the way they are? They can even help you track down some of those trilobites.